MLP as a universal approximator. We can represent any Boolean functions as a disjunction of conjunctions, and such a Boolean expression can be implemented by a multi-layer perceptron with one hidden layer. Each conjunction is implemented by one hidden unit and the disjunction by the output unit. For example, x1 exclusive XOR is equals to x1 and not x2 or not x1 and x2. We have seen previously how to implement and or using perceptrons. So two perceptrons can, in parallel, implement the two and another perceptron on top can OR them together. See figure 11.7. We see that the first layer maps inputs from the x1, x2 to the z1, z2 space defined by the first layer perceptrons. Note that both inputs 0, 0 and 1, 1 are mapped to 0, 0 in the z1, z2 space, allowing linear separability in this second space. Thus, in the binary case, for every input combination where the output is 1, we define a hidden unit that checks for that particular conjunction of the input. The output layer then implements the disjunction. Note that this is just an existence proof, and such networks may not be practical as up to 2 to the d hidden units may be necessary when there are d inputs. Such an architecture implements table lookup and does not generalize. We can extend this to the case where inputs are continuous to show that similarly. Any arbitrary function with continuous input and outputs can be approximated with a multi-layer perceptron. The proof of universal approximation is easy with two hidden layers. For every input case or region, that region can be delimited by hyperplanes on all sides using hidden units on the first hidden layer, a hidden unit in the second layer, then AND them together to bound the region. We then set the weight of the connection from that hidden unit to the output unit equal to the desired function value. This gives a piecewise constant approximation of the function. It corresponds to ignoring all the terms in the Taylor expansion except the constant term. Its accuracy may be increased to the desired value by increasing the number of hidden units and placing a finer grid on the input. Note that no formal bounds are given on the number of hidden units required. This property just reassures us that there is a solution. It does not help us in any other way. It has been proven that an MLP with one hidden layer with an arbitrary number of hidden units can learn any nonlinear function of the input. Figure 11.7 is the multilayer perceptron that solves the exclusive OR problem. The hidden units and the output have the threshold activation function with a threshold at 0.